Before discussing how to evaluate the severity of mitral regurgitation using color Doppler, let us see the Quanta effect. This Quanta makes regurgitant jets to become thinner and then create a false mild regurgitation, yet it might be much more severe. Here an example. The regurgitant jet in this case is relatively thin, though the regurgitation is severe, as we will discuss in another lecture. Why is it thin? Because it impinges on a valve leaflet or a wall and cannot get free from it. The best example of a Quanta effect is when you slowly turn a jar full of liquid. The liquid is not going to fall out of the jar straight from the edge. It will impinge on the side of the jar's wall and only fall at the end of it. The Quanta effect occurs due to a series of factors. Whenever a jet encounters a wall or a leaflet with a certain angle, it may get stuck to it. Because the jet has high velocity and hence low pressure, it makes the blood cells to be pulled into the jet since the pressure inside the left atrium is higher than in the jet. These cells increase the jet mass. However, this increase in mass only happens on the free surface of the jet. The other surface is trapped on the wall and there is no blood to join the jet, and then there is no increase in mass at this side. So the jet now consists of two layers, one at the free surface having more mass than the other at the wall. Now, there is a physical law called momentum conservation that says that within a closed system, always momentum is conserved. And what is momentum? It is mass times velocity. Then, if mass increases, the velocity must decrease. So the velocity of the upper free layer will decrease in relation to the wall's layer. Now comes another universal physical law, the conservation of energy, that says that within a closed system, the total form of energy must be conserved. In other words, if the velocity or kinetic energy of the upper free layer decreases, some other form of energy must increase. Then the pressure energy increases only in the free upper layer, pressing the lower layer against the wall where it cannot escape. That's the Quanta effect. Here is the case. A regurgitant jet started here, and if it were a central jet with no leaflet or wall constraint, it would be a large jet. However, it soon impinged on the posterior leaflet and later the left atrial wall and cannot get free, and the jet seems to be thin. See that the jet is thin here, but it extends laterally and medially, as seen in this short X showing the left atrium. It cannot spread to the center because of the pressure of the free layer, but it is a large jet spreading to the sides.